Welcome back, everyone, and we are very happy to have Alexey Sevastyanov from Aberdeen, and he will tell us about W-algebras, Mickelsson algebras, and Zhelobenko.
Thank you very much for the opportunity to talk here, such very beautiful place. So let me start with the items listed in the title. So firstly, I'm going to talk about q-algebras. They belong to a class, quite large class of algebras, which has some relations to the W-algebras mentioned by the previous speaker. But I'm going to consider kind of finitely generated toy versions of those algebras. Well, these algebras actually belong to a wide class of algebras, which I could call algebras of Hecke type. They are associated to the following data. Assume we have an associative algebra over some unitary. Then assume that we are given a subalgebra in it, equipped with a character. Then, given this data, we can associate another associative algebra. Namely, what we do, we take the one-dimensional representation induced by the character, then induce from this one-dimensional representation of the subalgebra A0 representation of A, and then consider the algebra of endomorphisms of this induced representation. Here it's the first line. And I consider it with the opposite multiplication for some technical reasons, which will be convenient. This convention will be useful later. So in the next line, there is another description of this algebra, which I will use later in my basic example. So namely, the induced representation of A can be also described as the quotient of A by the left ideal generated by the kernel, the character chi. And the algebra, which I call HK, after Hecke, of A0 chi, can be written using Frobenius reciprocity as the algebra of homomorphisms from the one-dimensional representation induced by the character to the induced representation, or in other words, it consists of classes in the quotient A over the ideal I, which are invariant with respect to the left action of the elements of the ideal. The importance of these algebras comes from the following fact. Consider an arbitrary A model E. Then, given this model, we can consider its subspace of A0 invariance, given here. And then this subspace is naturally a model of the algebra HK of A0 chi, because here you see we can compose endomorphisms of this induced representation with homomorphisms. So we obtain an action. On the other hand, if we are given a representation of this algebra HK of A0 chi, then we can induce a representation of the algebra A from it this way. So there are two functors acting between categories of representations of A and of the algebra HK of A0 chi. The point is that often in many examples, these two functors are usually inverse if you restrict them to appropriately chosen subcategories of representations. Well, the terminology, by the way, comes from the fact that when A is the group algebra of finite Chevalier group, A0 is the group algebra of a Borel subgroup in it, and chi is the trivial representation, then you obtain the classical Hecke-Vahori algebra this way. But I'm interested in a different story. So another class of important class of examples of these algebras come from the situation when A is the enveloping algebra of a semi-simple algebra, either over a field of complex numbers or a finite field. A0 then is the enveloping algebra of some nilpotent subalgebra, which is associated to nilpotent element, and chi is a character. This way we obtain the so-called finitely generated W-algebras. And then the equivalence here, if you, of course, restrict these two functions to appropriately chosen subcategories of representations, is called the Scrabble equivalence. Okay, I'm going to consider the situation when, as A, I choose a quantum group. So conceptually, there is some similarity between the finitely generated W-algebras and the objects which I obtain this way in case of quantum groups, but The Lie algebra situation, it's rather related to the study of gradings-only algebras. And in the quantum group case, these objects will be related to conjugacy classes in while groups. So roughly speaking, in the Lie algebra case, we deal with gradings. In the quantum group case, we deal with conjugacy classes in while groups. That's because quantum groups capture actually some properties of algebraic groups. And the study of algebraic groups is mainly the study of the periodic compositions, B and pairs, and things like that. Okay, so I'm only going to consider a very basic toy example of QW algebras because the general definition involves some very complicated combinatorics. So I'm only going to discuss one very basic, I would say simple example of QW algebras. So as I said, they are associated to, strictly speaking, conjugate classes of while group elements, but I'm only going to consider some very special case when my conjugacy class will be the conjugacy class of a Coxeter element. A Coxeter element is a product of simple reflections. So then I'm going to use a very special presentation of a Coxeter element. Namely, every Coxeter, the conjugacy class of every Coxeter element has an element which is represented as a product of two involutions. So it can be obtained in the following way. We take the Dynkin diagram of our underlying root system. Then you can consider the partition of this Dynkin diagram, of the vertices of the Dynkin diagram into two subsets, in such a way that the vertices in each of these subsets are not connected by edges. Then multiply simple reflections from each of these subsets. These reflections will compute with each other so that each such product will be an involution. And then the product of these two involutions gives you a Coxeter element, which I denote as here. Well, here I also denote by S1 the first involution, S2 the second involution. So these simple reflections SI1, SIN mutually compute, and SIN plus 1, SIL also mutually compute. So then I'm going to introduce some realizations of the standard Drinkel-Jimba quantum group, UQOG, which will be associated to while group elements. As I said here in this example, I only consider the Coxeter element, but in principle, the formulas which are written below here, they are true for any elliptic while group element S, which I will use a bit later. So for those who haven't seen these formulas before, probably they are not very informative. But I just would like to point out one important property. So here, LIs are roughly speaking Q to the power equal to the simple coovate generators in the Cartan algebra, roughly speaking. So, and these EJs and FJs play the role of simple positive and negative root vectors. So what's essential here is these quantum serial relations. Usually, if you're familiar with the structure theory of complex semi-simple algebras, the serial relations are written in terms of commutators. If you expand these commutators in the enveloping algebra, in the corresponding enveloping algebra, then you obtain such a homogeneous relation which will contain binomial coefficients. In the quantum group case, these binomial coefficients are replaced with Gaussian q-binomial coefficients. Well, these are defined using the usual formulas where all integers are replaced with q integers. I can also remind you the definition of q integer, which was given yesterday in the part we all solved. So, for instance, mq is q to the n minus q to the minus n, but q minus 1, although in these formulas here, this qi disappear with already some powers of q. Those curly brackets, those round brackets, sorry, denote just the scalar product of the Cartan algebra. Well, what's essential here is the appearance of these coefficients in front of the q binomial coefficients. Due to this property, a map which sends all generators Fi to some scalars will be a character of the subalgebra generated by Fi's. Well, when you apply this map to such a relation, these multipliers become not some constants. So let's assume that they are all non-zero. Then we are left with some weighted sum of q-binomial coefficients, which will be equal to 0 by the Gauss summation formula for the q-binomial coefficients. Well, for experts who are familiar with this quantum group theory, here is a statement how that representation of the quantum group is related to the standard Drinfeld-Jimbo presentation. So for that purpose, you have to choose an integer valued solution to this system of equations. TheseCij's are of very simple form. They are equal to the scalar products of simple roots times skew-symmetric matrix epsilon ij, the entries of which are equal to 1 if I is greater than j in the sequence of simple reflections I1, IL, which enter the definition of the Foster element, and -1 otherwise. So given a solution, an integer valued solution of such system of equations, we obtain an isomorphism of this or the algebra defined by the relations in the previous page and by the standard Dirichlet-Jimbo quantum group, and the isomorphism is given by these two formulas, by these formulas, which are pretty explicit. And as I already said, any map which sends generators Fi to some scalars is a character of this algebra generated by these Fi's. Well, now, once we have such a nice subalgebra inside of the quantum group, we could consider our threshold is A equal to the quantum group, A0 equal to the subalgebra generated by Fi's, and I equal to any of the characters introduced in the previous page, which characters send generators Fi to the scalars. I shall consider only the case when these scalars are all non-zero. But it turns out that this definition is not quite appropriate for our purposes. The point is that its behavior when q tends to 1 is not good enough. I mean, you can still introduce all the objects which I already mentioned, but they will not have nice properties. If you remember, the main motivation for the study of these algebras was a kind of equivalence result between two categories of representations of such an algebra of Hickey type and a category of representations of the algebra A. And to establish this kind of equivalences, we have to modify the definition slightly. Namely, instead of the quantum group, we have to consider the so-called locally finite part of the quantum group. That was introduced by Joseph quite a while ago, and is defined with respect to using the co-multiplication. Actually, quantum groups are off-algebra deformations of enveloping algebras. So let me define a slightly non-standard co-multiplication on the quantum group. Why do I modify the standard Dirichlet-Jimbo multiplication? It's because the subalgebra generated by Fi's becomes a left co-ideal. So if you look at these formulas for the co-multiplication, then on the right here, we have only generators of the subalgebra UQS of n, Fi's and this union. So then we can introduce two adjoint actions, the right adjoint action and the left adjoint action of the quantum group on itself, where I use the standard Swidler notation. And then we can, inside of the quantum group QQS of G, we can consider its locally finite part. It consists of all elements such that under the adjoint action of the quantum group, they generate finite rank subspaces. So this locally finite part is not a Hopf algebra, but it's still an associative algebra. And the main motivation for appearance of this object is that when q is equal to 1, it degenerates into the algebra of regular functions on the connected, simply connected algebraic groups associated to the same root system as the underlying algebra G I started with. So now what I'm going to do, let me recall my previously given definitions. I consider one-dimensional representation of my subalgebra UQS of n. So then I induce the representation of the quantum group. Here, this quantum group plays the role of A in my definition of TRHW algebras. UQS of n plays the role of A0. So this is the same as the quotient of the quantum group or the left ideal generated by the kernel of my character. And then let me denote by pi the projection of the quantum group onto this quotient. And let's consider the projection of the locally finite part onto the quotient. So then let me define the double algebra as the subspace of classes which belong to this projection, which I denote by CQ, which are invariant under the action of the left ideal generated by the kernel of chi. So this is exactly the initial definition which I gave here in the very first slide, with the only modification that now, instead of the entire algebra A, I consider some the image under phi of some subalgebra. So I think something smaller, but it's still an associative algebra. The point is that when I degenerate Q to 1, this CQ degenerates into the algebra of regular functions onto some closed subvariety of the Brillouin cell corresponding to the Y group element S. So that's the main motivation why we should replace the quantum group with its locally finite part. As I said already, the locally finite part itself generates into the algebra of regular functions on G. So it becomes commutative and it's isomorphic to the algebra of regular functions on G. So as you see, some Schubert calculus already appears at this stage. Well, once algebraic group appear, and at the quantum level we study some algebras of invariance, we would like to reduce the description of this invariance to invariance with respect to some group actions, at least at the classical level. This is done using the adjoint action. Namely, one can describe this QW algebra WQ as the algebra of invariance with respect to the adjoint action. The point is that the adjoint action of UQ of n is pushed down to this induced representation. This is again due to the fact that UQ as of n is left ideal. So you can push it down. This adjoint action of the quantum group can be pushed down to the action of CQ. And then proposition said that the QW algebra WQ can be described as the algebra of adjoint action invariance. Of course, it's a subalgebra in the A-type algebra I started with. But the use of this result is that when Q tends to 1, this adjoint action simply becomes the action induced by the conjugation action of the unipotent radical n on the closed subvariety, on this closed subvariety NSM. By S dot, by the way, I denote representative of the Y group element in group G. So, at least classically, when Q is equal to 1, we reduce the study of QW algebras to the study of conjugation action of n on some closed subvariety of the Brillouin cells, which is simply the conjugation action. So now, once we are interested in the invariance of this conjugation action, we have to look at the quotient. We have to look at the quotient of this variety n as n by the conjugation action of n. Well, the main result here is as follows. Let's consider the opposite unipotent radical of G, and let's consider the subgroup which consists of elements of n, which are conjugated to this opposite unipotent radical by a representative of the Y group with S. It's, by the way, in this example, an abelian subgroup, the dimension of which is equal to the rank of G. So then the theorem said that the conjugation action of n on n as n is free, and moreover, one can explicitly describe a cross-section, global cross-section for this conjugation action, which is in fact simply S times ns. so that the conjugation action gives you in fact an isomorphism of varieties. So this product of two varieties and S times n. Well, this theorem originally appeared in Steinberg's paper, quite old paper from 1965 on regular conjugacy classes in algebraic groups. This is because this cross-section S and S is in fact a global cross-section to the set of regular conjugacy classes. There is a deep generalization of this result to other conjugacy classes, to non-regular conjugacy classes, to myself, but as I said, I don't present it here because it requires quite complicated combinatorics. Well, by the way, Steinberg didn't prove this result in his paper. He only mentioned it, and I proved, in this case, I proved it much later, around 1998. Right, so now, classically, when Q is equal to 1, the Q double algebra is simply the algebra of n invariants on S times n, which is due to this isomorphism theorem, is simply the algebra of regular functions onto the slice sigma. Well, I would like to obtain now some explicit description of this algebra in the quantum case. At the classical level, this description is perfectly okay, but of course, at the quantum level, we don't have varieties. So we only have analogues of regular functions on these varieties. So we should somehow handle this problem in a different way. So firstly, I'm going to construct a natural projection operator from the algebra of regular functions onto S times n to the algebra of n invariant functions. This projection operator is quite natural. What you can do, take an arbitrary element y in your variety n, then you can uniquely conjugate it to an element of the slice sigma, right, by an element g of y, so that x of y belongs to sigma. So then one can define the following projection operator onto the space of n invariant functions. So you simply take an arbitrary function of n as n and evaluate its value at x of y. Right? So then this new function will be n invariant because when you conjugate this y by n, you don't change x of y, you only change g of y. So you obtain an invariant function. Well, I would like to obtain a quantum group analog of this projection operator. So for this purpose, let me describe this projection operator phi in a slightly different way. So n itself being unipotent radical, each element of n can be represented as a product of elements of one parameter subgroups corresponding to roots. So n, I can symbolically write as product n1 and so on, and d, where d is the number of positive roots in the root system. And then for the purposes of quantization, I have to choose a special order of these roots, namely, I'm going to choose the so-called convex order. In such an order, every root is written in between of its sums. So if a root gamma is the sum of two roots alpha and beta, then gamma is written in between of alpha and beta. And here is an example of such an order. Firstly, write all simple roots which appear in the definition of the Coxeter element S in the same order in which the simple reflections in the definition of S appear. So they are labeled by I1, IN, IN+1, IL. So, and then repeat this string until you reach the element number D. So then the point is that you can list all positive roots in delta plus in the following way. So call them beta 1, beta 2, and so on. Beta 1 will be the first root in this string. Beta 2 is S alpha, Si1, the reflection with respect to the first root applied to the second root, and so on until you reach the root number D. So let me also call WK the product of the first K simple reflections corresponding to the first K simple roots in this string of simple roots. So WK minus 1 applied to alpha IK gives you beta K. So then I can factorize my element G of phi, which appears here in the definition of the projection operator, as a product of elements corresponding to subgroups, one parameter subgroups corresponding to roots beta 1, beta 2, and so on. So this gives me a factorization of the projection operator. So the projection operator now will be represented as a composition of some operators, each of which is given by conjugation by an element of one of the one parameter subgroups. So I'm going to now give you an explicit formula for this projection operator. For the purposes of quantization, you need explicit formulas. So unfortunately, the only way to do quantum group theory is to get some formulas somehow, and then fiddle a little bit, play with coefficients until you get an appropriate quantum analog. So the operator will be written in terms of matrix elements of some finite dimensional representations that we denote by v mu, the reducible representation of G with highest weight mu, then by v small mu, a non-zero highest weight vector. So then I'm going to use the Chevalier involution on the group, which swaps the positive and negative group vectors. The maximum torus corresponding to the Cartan-Sobolev invariant. So I'm normalizing this. I'm normalizing the contravariant bilinear form on the finite dimensional representation in such a way that the scalar product of the highest weight vector with itself is 1. So then omega I defines fundamental weight, x beta is the root vector corresponding to beta, W is the readable while group, and then while group representatives act on the functions on G this way. So the action is induced by conjugation function. So here is the explicit description of the projection operator phi in terms of some matrix elements of finite dimensional representations. So firstly, let's consider the following rational functions. A priori, they have some denominators. What I do here, I take element s minus 1, conjugate it with the element w p minus 1 to the minus 1. I recall that this is simply product of the first p minus 1 simple reflections and this chain of reflections corresponding to simple roots which I use to define an ordering of the root system. So the point is that w p minus 1 to the minus 1 applied to the root w p is a simple root alpha I p. So that's why the conjugates of S appear, and I rather prefer to describe the conjugates of my projection operators phi p by these elements, because they will be given by conjugation by some elements of one parameter subgroups corresponding to simple roots. So each such conjugate, each such operator is induced by conjugation by some element of one parameter subgroup corresponding to the root alpha IP. And the coefficients in this one parameter subgroup are given by these a priori irrational functions. But the point is that, in fact, if you compose all these operators all together like this, then these denominators will cancel. So it's not very big miracle, actually. All right, so now I have these explicit formulas for the projection operators phi p and for the projection operator p. So now I'm going to describe a quantum analog of these formulas. So for this purpose, I need, I need another object. Actually, if you look at this formula, then you can discover that these operators, phi p, are expressed in terms of conjugation operators, which may have very nice quantum group analogs, because if you expand these exponentials in the conjugation, using the usual exponential series, you obtain a kind of exponential of the adjoint action. So I have a quantum group analog of the adjoint action. And then I also have these divisions AP, which are expressed in terms of matrix elements of finite dimensional irreducible representations. So I need operators of multiplication, quantum group analogs of operators of multiplication by these divisions. Well, these analogs naturally appear in the restricted or Hopf algebra dual to the quantum, which is by definition the Hopf algebra generated by matrix elements of finite dimensional representations of q. But of course, as an algebra, this algebra is quite different from the quantum. The point is that one can still introduce an adjoint action on it induced by the adjoint action of uq of G on the quantum group. And then there is an isomorphism of the restricted dual and of the locally finite part of the quantum group. It's actually given by pretty explicit formula related to the fact that the formal series, power series version of the quantum group is quite triangular. So it's given in terms of a universal R matrix. This result is originally due to Joseph, with some more explicit formulations by Schmidt or Paul Stockman. So anyway, here is the formula. That's just a remark for experts. So what does it mean that we have this isomorphism? We can translate some operations from the locally finite parts to the restricted dual and vice versa. Well, now I would like to describe everything using the restricted dual, because I already have an adjoint action on it, and I also have an analog of matrix elements of finite dimensional representations, right? And I have dimensional multiplication. So what I would like to do, I would like to now describe an analog of the ideal IS on the side of the restricted dual. Of course, because this Joseph isomorphism acts in one direction only, somehow I have to guess how it looks like on the side of the restricted dual. And this will be actually more or less the ideal, the quantum analog of the vanishing ideal of Schubert variant. So it's simply generated by matrix elements of some finite dimensional reducible representations of this form, where V omega is the highest weight vector and some irreducible finite dimensional representation, and psi satisfies this property. So then the result is that the image of this ideal under psi projected by pi onto this module is equal to 0. So at least this ideal JS it's not larger than my ideal IS, and it turns out that it's already enough. It's big enough already. So now let me denote the quotient of the restricted dual by this ideal, by this symbol, which stands actually for the quantum analog of the algebra of regular functions on the quantum Schubert variety, so based on the S. So we obtain a subjective homomorphism from this quotient to CQ, and in fact it's a homomorphism of the modulus with respect to the adjoint action of UQ of M. Well, now here are the formulas for the quantum analog of the projection operator phi. Well, what I have to do actually, because if you remember in the classical formulas, I had some denominators, I have to localize this quantum Schubert variety a little bit to get the quantum analog of the algebra of regular functions in quantum Schubert itself. It's a right localization. So because all algebras become now non-commutative, I have to distinguish between left and right localization. So I can consider the right localization here. Then these BPs are analogs of APs in the classical case. And then these operators PP are analogs of pi p in the classical case. If you compare these formulas with the classical formulas, they are roughly obtained by some extrapolation of the expansions of the exponentials here using the Taylor series. which will give you some powers, expansion in powers of the adjoint action. And then you multiply by these coefficients BP by powers of these coefficients BP from the right. Again, here everything is not immediate, so we have to distinguish between left and right multiplication. So now, in this particular case, if we consider the composition of these operators, which will be now twisted by compositions of braid group automorphisms with some other automorphisms. Well, simply speaking, they are not automorphisms, they are just maps of models of the ground plane. These are quantum corrections which you cannot see in the classical case. If experts are interested, I can give a bit more details. They appear basically because the braid group actually doesn't commute with the adjoint action for quantum groups. So you need to introduce these quantum corrections. And finally, what is the image of this projection operator P in this case? Well, this is simply the center of the quantum group. In general, by the way, these denominators will not cancel in more general examples. So you will obtain some localizations of W-algebras in this case. And as an exercise for students, you can try to do some calculations in the case of SL2 and verify that if you apply this projection operator to this matrix element, then up to a square multiple, you obtain the class of the Casimir in Q of SL2. Okay, thank you. Sorry, I'm out of time with it.
A very nice question is that you started doing the certain chapter, the non-degenerate chapter. You started doing the non-degenerate chapter.
Yes.
Okay. And the reducing algebra does not depend on this part.
Well, not essentially. I mean, these coefficients Ci in the definition of the must be non-zero.
Yes.
Yeah, they are the only essential requirement.
I see. So it's a concept.
Yeah, yeah. If you change C, then I think you can somehow absorb it by applying something more.
Any flexible loop or specialization? Specialization?
Oh, I swapped under the carpet a little bit these details. Well, to begin with, here, you actually have to consider the continuing cut form, which means that these elements containing some denominators are regarded as new generators. Then when you specialize Q to 1, you obtain some central elements. Actually, Li becomes central. If you then factorize by the relations which send these Li's to 1, then you obtain the invariant. Well, again, the adjoint action, it's a bit tricky also. How can you specialize these formulas to 1, these quantum formulas, if they contain some denominators? Yeah, you see, but the point is that they only contain ratios of these root vectors and of these denominators, and these ratios belong to the realistic form. So somehow the adjoint action can be actually defined on the realistic form. The realistic form acts by the adjoint action on the continuous cut form, and then you can specialize everything to Q equal to 1.
And Q,
Huh?
and Q.
Yes, you can also specialize it to Q being a root of unity. Then all these infinite series become truncated. Right. And actually, these coefficients BP, they play a very important role in the proof of the continuous procedure conjecture, roughly speaking. Truncated polynomials and powers, truncated monomials and powers of these BP, they form a basis of finite dimensional reducible representations, power representations of W-algebras. Yeah, so I spoke many technical details under carpet here. It's not that easy as it looks like in this presentation.
So if there are no more questions, let's check it here.